The universe is not a random scattering of stars, but a vast, intricate web. This cosmic web, a network of galaxies and dark matter stretching across billions of light years, is the grand architecture of everything. Yet woven into this tapestry is a single, bizarre anomaly, a knot so strange and dense it defies our fundamental laws of physics. By the end, you will understand why this one cosmic structure has the potential to rewrite the rules of how our universe evolves. Astronomers are staring at data that suggests gravity itself might be broken there, and that the heart of this cluster is burning with a star-forming fury that should be impossible. What does it feel like to discover something that makes no sense? This immense structure is the universe's very skeleton, a blueprint written in galaxies and shadow. Picture the night sky not as a flat sheet of stars, but as a three-dimensional tapestry. Within it, galaxies are not scattered randomly like tossed salt. They are strung along immense, thread-like highways of dark matter and hot gas, structures we call filaments. These filaments can stretch for hundreds of millions of light years, weaving together to form a colossal web. And where these threads cross and tangle, they create dense, bustling hubs, the knots of the cosmic web. Between these brilliant strands lie the voids, unimaginably vast deserts of near-nothingness, so empty that if our Milky Way sat in the center of one, we might not have known other galaxies existed until the 1960s. It is a structure of breathtaking beauty and order, resembling a neural network for a brain the size of everything, or a spider's web spun on a scale beyond human comprehension. This architecture did not appear by chance. Its origins are written in the first moments of time. In the furious heat just after the Big Bang, the universe was a searing, nearly smooth soup of energy. But within that smoothness, thanks to the strange rules of quantum physics, tiny ripples of density were inevitable, random fluctuations on a subatomic scale. Then, inflation happened. In a fraction of a second, the universe underwent a growth spurt of impossible speed, stretching those quantum ripples across the cosmos, etching them into the very fabric of space-time as faint blueprints. For billions of years, gravity acted as the master sculptor. It patiently pulled matter, both the visible kind we see and the mysterious dark matter we cannot, toward those slightly denser regions. Gas and dust flowed along the emerging lines of force, condensing into stars and galaxies along the filaments, while the emptier regions drained further, becoming the voids. So the cosmic web we see today is the final, majestic result of a 13.8 billion-year-long construction project, starting with quantum whispers and ending with a universe-spanning net. To understand the universe's story, then, we must study its structure. And the most critical chapters of that story are written at the intersections in the dense, chaotic, and incredibly active knots where the web's threads pull tightest. Deep within this grand design, astronomers found a knot that should not exist. It carries the formal designation SPTCLJ 2344-4243, a name better suited for a catalogue than a cosmic mystery. Most know it by a more evocative title, the Phoenix Cluster. Located a staggering 5.7 billion light-years away in the direction of the constellation Phoenix, this is not merely a cluster of galaxies. It is a monstrous confluence where multiple thick filaments of the cosmic web have drawn together and pulled tight, creating a gravitational nexus of almost incomprehensible scale. Imagine the busiest, most chaotic intersection in the universe, a galactic mega-city where the traffic laws of physics appear to have been suspended. The Phoenix Cluster earns its status as a true knot, first through sheer, staggering mass. It is one of the most massive objects we have ever identified, containing the equivalent of several quadrillion suns. That mass is not just in its thousands of member galaxies, but is dominated by a seething ocean of superheated gas that glows with the power of 1 trillion suns and a vast halo of the invisible glue of dark matter. This alone makes it a titan. But the real mystery, the reason it keeps astrophysicists awake at night, is not just how much stuff is there, but what that stuff is doing. According to every established model, a cluster this old and this massive should be quiet, settled, and dormant. Its central giant galaxy should be a red and dead elliptical, having long ago consumed all the cool gas needed to form new stars. The Phoenix cluster did not get the memo. At its heart rages a stellar nursery of impossible intensity, birthing new stars at a rate hundreds of times faster than our own Milky Way. It is a cosmic furnace, burning with a fury that defies all expectations. This bizarrely high activity suggests the rules governing how these colossal structures live and evolve are either incomplete or, in this specific tangled knot of space-time, fundamentally broken. The discovery began not with a dramatic image, but with a subtle distortion in the cosmic microwave background. In 2010, data from the European Space Agency's Planck satellite, which was mapping the faint afterglow of the Big Bang itself, revealed a profound shadow. It was a spot on the sky where the microwave light was being absorbed, a telltale sign of the Sunyaev-Zeldovich effect. This occurs when the hot electrons in a massive galaxy cluster scatter the ancient cosmic microwave photons, leaving a cold imprint. The Planck data indicated something colossal was there, a gravitational well so deep it was bending the light from the universe's infancy. This shadow pointed the way, and astronomers turned the powerful South Pole telescope toward the coordinates. Its microwave eyes confirmed a massive object, a knot of incredible density 5.7 billion light-years away. But it was what happened next that truly ignited the mystery. When the Chandra X-ray Observatory, NASA's premier X-ray telescope, focused on the spot, it did not see a typical, relaxed cluster. Instead, Chandra saw a blazing, roiling cauldron of gas. The central galaxy was pouring out X-rays at an intensity that was off the charts, indicating a core that was not cold and dead, but violently, impossibly active. The initial reaction among the teams analyzing this data was a mixture of profound excitement and deep confusion. Here was a cluster that, by its mass and age, should have settled into a quiet middle age billions of years ago. Yet the data screamed youth and ferocity. It was like finding a massive, ancient redwood tree that was, against all logic, sprouting vibrant new leaves at a rate faster than a sapling. The more observations they gathered from optical and infrared telescopes, the stranger the picture became. The central galaxy was not the expected red dead elliptical, but was instead blazing with the blue light of countless newborn stars. Each new dataset deepened the contradiction, transforming a curious anomaly into a full-blown cosmic paradox. The Phoenix cluster was not just a knot in space, it was a knot in our understanding. The numbers associated with this knot are not just large, they are vertigo-inducing. The Phoenix cluster contains a mass equivalent to several quadrillion suns. To grasp that, consider our own Milky Way galaxy, home to hundreds of billions of stars. This single cosmic knot holds more mass than if you took 1,000 Milky Ways, ground all their stars, gas and dark matter into a paste, and packed it into a region of space only about 5.5 million light-years across. It is a density of matter that challenges the imagination. But how do we even weigh something so impossibly distant? Astronomers use a trio of cosmic scales. First, they observe gravitational lensing, the way the cluster's immense gravity bends and distorts the light from galaxies far behind it, like a flaw in a giant lens. The amount of distortion directly reveals the total mass, causing the warp. Second, they measure the velocities of the thousands of galaxies orbiting within the cluster's grip. Just as the speed of planets tells us the sun's mass, the frantic orbits of these galaxies reveal the gravitational pull at the cluster's heart. Third, instruments like the Chandra X-ray Observatory map the superheated gas that fills the space between galaxies. The temperature and pressure of this million-degree plasma, held in place by gravity, provide another precise measurement of the cluster's mass. All three methods converge on the same staggering figure. Yet the mystery deepens because it is not just the amount of mass that is puzzling, but its configuration. In our best supercomputer simulations of how the cosmic web forms, such an extreme concentration of mass, assembled so early in the universe's history, is vanishingly rare. It suggests this knot did not form through the slow, steady accumulation of matter along filaments. Instead, it hints at a far more violent and rapid birth, a catastrophic collision or a freakish confluence of multiple cosmic highways all at once, packing the universe's matter into a gravitational anomaly that our models can scarcely produce. This is the first clue that we are not just looking at a big object, but at a statistical outlier, a cosmic jackpot winner that by all rights should not exist. The heart of this impossible knot is a galaxy that defies every expectation. This is not a quiet, aging giant, but a cosmic furnace of unimaginable ferocity. Known as the brightest cluster galaxy, or BCG, it sits at the gravitational center of the Phoenix cluster, a position that should guarantee a serene and uneventful retirement. Instead, it is a ravenous, hyperluminous beast. While a typical galaxy like our Milky Way forms about one new star, the mass of our Sun each year, this central monster is forging new stars at a rate of over 700 solar masses annually. That is the equivalent of creating 2 stars like our Sun every single day. This is a level of stellar creation unseen in the core of a massive cluster for over 10 billion years. A frenzied pace that belongs to the universe's chaotic youth, not its settled middle age. The paradox is profound. The entire cluster is filled with an ocean of superheated gas, plasma so incredibly hot it glows in X-rays. According to all established physics, this seething intracluster medium should act as an impenetrable barrier. It should prevent any cooler gas from reaching the central galaxy, effectively starving it of the fuel needed to make new stars. In most mature clusters, this is exactly what happens, leaving the BCG a red and dead relic. But here, the rules have broken down. The Phoenix cluster's core is experiencing what astronomers call a runaway cooling flow. Imagine a pot of water boiling violently on a stove, with steam rising in a chaotic plume. Now imagine that, against all logic, some of that steam suddenly condenses back into cold droplets and falls directly back into the center of the flame. That is the baffling process happening on a galactic scale. Somehow, the superhot gas in the cluster's heart is cooling rapidly and catastrophically, collapsing inward in a torrential rain of cold fuel directly onto the central galaxy. This is a cooling flow anomaly on cosmic steroids, a process so extreme and efficient it is resurrecting a dead giant into a stellar newborn. It forces a startling question. What cosmic switch was flipped inside this tangled knot, allowing a dormant engine to roar back to life with such violent intensity? This superheated plasma is the key to the entire mystery. The space between the galaxies in the Phoenix cluster is not empty. It is filled with an immense ocean of gas, the intracluster medium, heated to a staggering 50 million degrees. To hold that kind of heat, the gas must be under immense pressure, which comes from the crushing gravitational weight of the entire knot. For decades, our understanding was clear and consistent. In a massive, mature cluster, this hot gas halo should be stable. It should act like a perfectly insulated blanket, keeping the core in a state of hot, quiet equilibrium. X-ray telescopes like Chandra have mapped this seething plasma in exquisite detail, revealing its intricate structure and confirming its mind-bending temperature. The gas glows so brightly in X-rays that from 5.7 billion light-years away, it outshines every other source in the region. This is the expected behavior for a cosmic titan of this age. Yet, when astronomers looked closer at the data, they saw something that shattered that simple picture. Embedded within that blazing halo were clear, unmistakable signatures of gas that was not hot, but cool. Filaments and tendrils of material mere millions of degrees instead of tens of millions were detected spiraling down toward the central galaxy. This is the phenomenon known as a cooling flow. The idea is straightforward. Even in that hot gas, a tiny amount of energy can radiate away, mostly through X-ray emission. As it loses energy, the gas cools, becomes denser, and should slowly drizzle inward under gravity, providing a gentle trickle of fuel to the central galaxy. In most clusters, this process is either completely shut off or so slow it's negligible. But in the Phoenix knot, the drizzle has become a catastrophic downpour. The cooling is not gentle or slow. It is happening at a rate hundreds of times faster than any theoretical model predicted was possible. The hot gas halo is not stable at all. It is experiencing a rapid, runaway collapse in its very center. This creates a vicious and beautiful cycle. As the cold gas rains down, it feeds the insane star formation in the central galaxy. Those newborn stars, along with the activity of the supermassive black hole at the galaxy's heart, then blast out energy and turbulence. That energy should reheat the surrounding gas, shutting off the cooling flow. This is the feedback loop that governs all galaxies. But here, the loop is broken. The heating is somehow insufficient or misdirected, failing to stop the cooling cascade. The result is a system wildly out of balance, where the fuel supply is wide open and the stellar engines are running at full throttle. This runaway process is what makes the Phoenix cluster not just an anomaly, but a glaring error in our cosmic calculations, a place where the universe's standard thermostat has catastrophically failed. At the very center of this stellar maelstrom lies an even deeper enigma, a gravitational anchor holding the entire chaotic knot together. This is the supermassive black hole, a cosmic beast with a mass billions of times that of our Sun. In every other massive cluster we have studied, a black hole of this scale acts as the ultimate regulator. It is the universe's built-in thermostat. As cold gas rains into fuel star formation, some of that material inevitably spirals into the black hole's accretion disk. This process does not quietly swallow matter, it unleashes titanic energies. The black hole erupts, blasting out colossal jets of radiation and particles that travel for hundreds of thousands of light years, reheating the surrounding gas and slamming the brakes on further cooling. This feedback loop is elegant and self-balancing, preventing any galaxy from growing too large, too fast. But in the Phoenix cluster, this thermostat appears to be broken, or at least working on a baffling delay. Observations show clear evidence that the central black hole is active. We can see the faint, ghostly cavities carved in the hot X-ray gas by its powerful jets, bubbles of energy that have pushed the searing plasma aside. The problem is one of scale and timing. These jets, while powerful, seem strangely anemic compared to the catastrophic cooling flow they are supposed to counteract. It is as if a forest fire is raging out of control and the fire department has arrived but is only spraying a garden hose. The heating is happening, but it is insufficient, misdirected, or out of sync with the cooling cascade. This failure of feedback is the core of the knot's mystery. Why is a billion solar mass black hole, an engine of unimaginable power, losing its battle against a simple flow of cooling gas? The answer may lie in the chaotic nature of the knot itself. Perhaps the infalling gas is so turbulent and clumpy that the black hole's jets cannot establish a stable heating influence. Or maybe the cooling is simply happening too fast, overwhelming the black hole's ability to respond. This broken feedback loop is not just a quirk of one cluster. It challenges our fundamental understanding of how the most massive structures in the universe regulate their own growth. If the cosmic thermostat can fail so spectacularly here, in this one tangled knot, what other rules might be quietly breaking elsewhere in the cosmic web? This bizarre knot may be a relic from the universe's most violent youth. Its extreme properties lead some theorists to a radical possibility that the Phoenix cluster is not a product of standard cosmic evolution, but a primordial anomaly. Perhaps it was born from a seed of unimaginable density. In the first fleeting moments after the Big Bang, quantum fluctuations created tiny ripples in the fabric of everything. Most were minor wrinkles, but what if, by a 1 in a trillion chance, one of those ripples was not tiny at all? What if it was a colossal spike, an ultra-dense knot in the quantum foam itself? When inflation stretched the universe, this spike would have been magnified into a region of preposterous density, a gravitational well so deep it began pulling in matter at a ferocious rate. From the very beginning, this would make the cluster not just massive, but anomalously so. A cosmic dinosaur that grew to titanic size because it started with a head start no other structure had. It would be a fossil, not of galaxies, but of the universe's own initial conditions, preserved in the amber of space-time. A more dynamic, though equally catastrophic origin story involves a traffic accident on a cosmic scale. We know clusters often grow by merging, two massive structures colliding over billions of years. But what the Phoenix cluster represents might be something far more extreme, a major merger of not two, but perhaps 3 or 4 of the thickest filaments of the cosmic web all at once. Picture the universe's largest highways, each streaming with galaxies and dark matter, converging on a single intersection at nearly the same time. The resulting pileup would be a gravitational cataclysm of unbelievable energy, shocking vast reservoirs of gas, funneling them into the center and igniting a firestorm of star formation that our models, which typically simulate gentler mergers, simply cannot replicate. This scenario paints the knot not as a quiet fossil, but as the site of the most dramatic crash in its corner of the cosmos. A pileup whose wreckage is still glowing with the heat of impact and birthing new stars from the scattered debris. Its present state offers another clue to its past. The insane star formation and runaway cooling we see might be a temporary, if spectacular, phase. Some scientists speculate that the Phoenix cluster could be caught in the act of becoming what is known as a fossil group. In the distant future, after its current burst of activity, the central galaxy will have consumed all the nearby fuel in the surrounding smaller galaxies. Through a process called dynamical friction, these smaller galaxies will slowly spiral in and be swallowed by the central giant. What will remain is a single, monstrous, elliptical galaxy, sitting in splendid isolation at the heart of an immense dark matter halo, a fossil of a bygone era of violence. The Phoenix cluster may be showing us this process in its most extreme, accelerated form. It is a living snapshot of a transition that most clusters underwent gently, billions of years ago. This makes it a unique time capsule, a window into an epoch when the universe was a far more chaotic and violent place, a window we thought had closed long ago. The existence of such a knot forces us to wonder if our cosmic timeline is too neat, and if other primordial holdouts, other rule-breaking anomalies, are waiting to be found in the web's darkest tangles. This broken thermostat reveals a war raging at the heart of the knot. On one side, you have the furious birth of stars, a process that demands vast reservoirs of cold, dense gas. On the other, you have the active galactic nucleus, the AGN, the supermassive black hole at the galaxy's core. When matter spirals toward this gravitational abyss, it does not go quietly. The material forms a screaming, superheated disk before falling in, and in the process, it unleashes beams of energy that can punch clear across the cluster. These are relativistic jets, torrents of charged particles moving at nearly the speed of light. They carve immense, ghostly bubbles in the surrounding hot gas, cavities that we can see in X-ray images. In a perfectly balanced system, this is the universe's regulations mechanism. The energy from these jets heats the surrounding gas, preventing it from cooling and falling in to make more stars. It is a beautiful, self-correcting loop, a cosmic thermostat that keeps giant galaxies from growing out of control. But in the Phoenix cluster, the thermostat is shattered. The cooling flow and the stellar nursery are running wild, and the black hole's jets, for all their power, seem incapable of stopping them. It is a battle where one side is inexplicably losing. So what could cause such a fundamental failure? One possibility is a simple matter of aim. The jets from an active galactic nucleus are not omnidirectional showers. They are focused beams, like lighthouse beams or the precise streams from a fire hose. If those beams are pointed in the wrong direction, if they are not aligned with the densest pockets of cooling gas, then their immense energy might be wasted, shooting off into the voids of intergalactic space instead of reheating the fuel supply. Imagine trying to put out a kitchen fire by spraying water out the window. The power is there, but it is not hitting the target. Another, more unsettling possibility is that the cooling inflow itself is simply too much to handle. The rain of cold gas onto the central galaxy might be so torrential, so overwhelming, that even a perfectly aimed AGN cannot vaporize it all. Some of the fuel slips through, reaching the stellar nurseries and feeding the frenzy. This suggests a system so far out of equilibrium that our standard models of feedback have no answer for it. The presence of the AGN jets proves the black hole is active and trying to do its job. The presence of runaway star formation proves it is failing. This imbalance is the central throbbing contradiction of the knot, a place where the most fundamental rule of galactic regulation has been suspended, leaving us to wonder what other cosmic laws might be quietly bending in the dark. The galaxy populations trapped within this knot are a cosmic archaeological dig. If we could zoom in with the piercing gaze of the Hubble or James Webb Space Telescopes, the view would be one of controlled chaos. Not just one or two galaxies, but hundreds, perhaps thousands, swarm within the cluster's core. There are massive, smooth ellipticals, golden-hued relics that finished their star formation eons ago. Alongside them, spiral galaxies, their delicate arms often twisted and distorted by the immense gravitational tides of their neighbors. Dwarf galaxies, faint smudges of light, orbit like moths around street lamps. Every one of these objects is a prisoner of the knot's gravity, moving at thousands of kilometers per second on orbits that will take hundreds of millions of years to complete. This crowded metropolis is the environment where galaxies are forged, broken, and transformed. The key to understanding the knot's history lies not just in counting these galaxies, but in reading the light they emit. Astronomers perform a galactic census, analyzing their colors. A galaxy's color is a direct indicator of its star-forming health. Galaxies brimming with hot, young, massive stars glow with a blue light. Those whose star-forming gas has been stripped away, leaving behind only older, cooler red giants, emit a characteristic red hue. In a typical mature cluster, the environment is a galactic graveyard. The dense, hot gas between galaxies acts like a cosmic sandblaster, physically stripping away the cool gas reservoirs from infalling spirals in a process called ram pressure stripping. The violent gravitational interactions can tear galaxies apart or trigger bursts of star formation that quickly exhaust their fuel. The expected result is a population dominated by red, dead ellipticals. But the Phoenix knot is not typical. The census here reveals a shocking number of blue, star-forming galaxies intermingled with the red relics. This is a vital clue. It suggests that the extreme environment of this particular knot has not yet finished its quenching work. The presence of so many blue galaxies indicates a younger, more dynamic assembly history. It means that fresh spirals are still falling into the cluster along the cosmic web filaments, bringing new fuel with them, and that the cluster's ferocious core activity might even be triggering star formation in some satellites through shock waves and compression. This mixed population paints a picture of a knot caught in a dramatic transition, a work in progress where the usual rules of galactic suppression are being overwhelmed by a torrent of incoming material. The galaxies themselves are telling us that this is not a settled, ancient structure, but a living, breathing, and still forming cosmic entity. The immense gravity of this cosmic knot warps space itself, creating a powerful natural telescope. This phenomenon is called gravitational lensing, and it turns the Phoenix cluster into a unique window on the universe's earliest epochs. Einstein's theory of general relativity tells us that mass curves the fabric of space-time. Light, traveling through this curved space, does not move in a straight line, it bends. An object as massive as this cluster acts like a colossal lens in space, distorting and magnifying the light from galaxies that lie far behind it. What we see are not clear images of those distant objects, but stretched, smeared, and often duplicated arcs of light, celestial mirages painted across the sky. Around the Phoenix cluster, astronomers have identified dozens of these faint bluish arcs, graceful curves that trace the contours of its immense gravitational well. In a few rare cases, when the alignment is perfect, the lensing creates a complete circle of light known as an Einstein ring, a halo of warped starlight that marks the precise edge of the lens's strongest focus. These are not flaws in the observation. They are signatures of the knot's power, bending light from sources otherwise far too faint and distant for any human-built telescope to see. This cosmic lens offers an extraordinary gift. The magnified galaxies we see through it are not contemporaries of the cluster. They are time travelers. Their light began its journey toward us long before the Phoenix cluster itself even fully formed over 10 billion years ago during the universe's formative years. By studying these distorted yet amplified images, astronomers can peer back to an era known as the cosmic dawn, when the first galaxies were assembling out of the primordial darkness. The lens does more than just make these objects brighter. It acts like a natural zoom lens, revealing intricate details about their structure, their rate of star formation, and their chemical composition that would be utterly impossible to discern without this gravitational assist. It is as if the universe, in creating this mysterious and rule-breaking knot, also placed a powerful magnifying glass directly in front of our most distant past. So while we struggle to understand the knot's own bizarre physics, we can simultaneously use its immense gravity as a tool to unlock other cosmic secrets. This transforms the Phoenix cluster from a mere anomaly into a vital cosmic laboratory. Its very existence, a knot of contradictions, also provides a serendipitous portal, allowing us to witness the faint glow of infant galaxies whose light has been carried and focused across the void by the knot's own impossible weight. To truly grasp the strangeness of this knot, we must place it on the cosmic stage alongside other legendary heavyweights. In one corner, we have El Gordo, the Fat One, a colliding cluster over 7 billion light-years away. Its claim to fame is raw, staggering mass and the searing heat generated by a violent merger, a cosmic train wreck caught in the act. In another corner stands the Bullet Cluster, famous not for what we see but for what we do not. Its collision cleanly separated normal matter from dark matter, providing some of the strongest visual evidence that dark matter is real. Then there is the Phoenix cluster itself, a namesake and a close cousin to our mystery, renowned for its shocking central star factory. Each of these champions excels in one specific, extreme trait. El Gordo is the undisputed king of merger violence. The Bullet Cluster is the master of revealing dark matter's secrets. The Phoenix Cluster holds the title for runaway star birth in a mature giant. Our mysterious knot, however, refuses to be confined to a single category. It appears to be a contender for the championship in all of them at once. Preliminary measurements suggest its total mass may rival or even surpass El Gordo's, making it a gravitational titan. Its core gas temperatures are among the highest ever recorded, pointing to incredible internal energy. Its star formation rate, if confirmed, could challenge the Phoenix Cluster's own record. And its supermassive black hole activity shows the same baffling, ineffective feedback loop. This is what separates it from every other extreme object we know. Where others break one rule, this knot seems to be breaking the entire rule book. It is not a specialist, it is a freak of nature, a cosmic polymath of anomalies. Imagine an athlete who simultaneously holds the world records for the 100-meter dash, the marathon, and the heavyweight lift. That level of all-around supremacy defies our understanding of specialization and limits. In the universe, such comprehensive outliers are not just rare. They are profound puzzles. They suggest that our models of structure formation might be missing a fundamental ingredient, a process, or an initial condition that allows for a single object to become extreme in every possible way. This knot is not merely massive or hot or active. It is all these things in a terrifyingly perfect storm, cementing its status not just as a heavyweight, but as the most mysterious champion in the cosmic arena. But a hidden force might be threading this chaotic system together. Beyond gravity and heat, another invisible player shapes the knot's destiny, the subtle but pervasive influence of magnetic fields. These are not the simple bar magnets from a school experiment, but vast, dynamic webs of energy woven through the superheated gas and between the galaxies themselves. They are the cosmic equivalent of the lines you see when ion filings arrange themselves around a magnet. Only these lines stretch for millions of light years, guiding charged particles and potentially holding the entire turbulent mess in a strange kind of order. Mapping these fields is a monumental challenge, requiring some of the most sensitive radio telescopes on Earth, like the Atacama Large Millimeter Array, or ALMA, and observations of polarized light. When light or radio waves pass through a magnetized region, their orientation can be subtly twisted. By meticulously measuring this polarization, astronomers can trace the otherwise invisible magnetic field lines, revealing their strength and direction. It is like listening to a whisper in a hurricane, but the whispers are telling us the secrets of the knot's internal wiring. What they might reveal in this particular knot could be the key to its cooling crisis. The magnetic environment here is likely not just strong, but fantastically tangled. Picture a ball of yarn after a kitten has played with it for hours, a chaotic snarl of loops and knots on an astronomical scale. Such a field could act as a cosmic funnel, channeling the flow of cooling gas along specific magnetic highways directly toward the central galaxy, making the cooling rain more efficient and organized than gravity alone could manage. Conversely, these same magnetic fields might be acting as a superb insulator. The superheated gas in the cluster loses energy through conduction, with heat flowing from hotter regions to cooler ones. But a powerful, tangled magnetic field can severely inhibit this process. It can trap particles, preventing them from moving freely and carrying thermal energy away. If the knot's magnetic fields are exceptionally strong, they could be corking the bottle, preventing the heat from the outer regions from flowing inward to rewarm the cooling core. This would directly exacerbate the runaway cooling flow, creating a perfect storm where cold gas falls in unimpeded because the heat cannot get where it needs to go to stop it. This introduces a non-thermal component to the physics, a layer of complexity beyond simple temperature and gravity. Magnetic fields can also confine and accelerate cosmic rays, ultra-high-energy particles that streak through space. These rays add another form of pressure and energy to the intracluster medium, potentially stirring the gas or providing alternative heating mechanisms. Could it be that the knot's bizarre state is not just a failure of the black hole thermostat, but a magnetic takeover? A place where magnetic forces have become so dominant they have overridden the standard thermal rules of cluster evolution. Untangling this magnetic web, if it can be done, might finally explain how this cosmic knot tied itself into such an impossible configuration, holding the universe's most energetic contradictions in a single, magnetized grip. The most advanced supercomputers on Earth are wrestling with this knot, and they are losing. To understand what is happening in a place like the Phoenix Cluster, astrophysicists do not just build telescopes. They build entire universes inside machines. Projects like illustrious TNG and the 300 project use some of the world's most powerful supercomputers to simulate the birth and evolution of the cosmic web, from the first flickers after the Big Bang to the present day. These are not simple animations. They are breathtakingly complex digital experiments governed by all the known laws of physics, tracking the gravitational dance of trillions of particles representing dark matter, gas, and stars. The results are stunning visualizations that show vast cosmic webs forming, with filaments, voids, and clusters emerging in beautiful, swirling detail. You can watch a simulated cluster, a digital knot, grow over billions of years, pulling in matter and merging with its neighbors. When you place a side-by-side comparison of a typical simulated massive cluster and a real image of the Phoenix knot, the broad strokes match beautifully. Both show a dense central hub, a sprawling halo of hot gas, and a swarm of satellite galaxies. This is a triumph of modern cosmology, proving our foundational understanding of structure formation is largely correct. But then you zoom in on the details and the simulation begins to fray. In the digital universe, when a cluster reaches the mass and age of our mysterious knot, its central galaxy is almost always a quiet, red, and dead giant. The supermassive black hole at its heart has effectively done its job, heating the surrounding gas and shutting down star formation. The simulations can produce massive clusters, and they can even produce clusters with strong cooling flows, but they struggle catastrophically to produce a cluster that has all three extreme properties at once: the staggering mass, the runaway cooling, and the explosive central star formation. To make a simulation spit out something that looks even remotely like the Phoenix Cluster, programmers have to engage in what is called fine-tuning. They must manually adjust parameters, like the efficiency of the black hole's feedback or the rate of gas cooling, to unnatural levels. It is like forcing a recipe to work by adding 10 times the normal amount of every ingredient, a solution that feels more like a cheat than an explanation. This gap between the clean, governed universes inside our computers and the messy, rule-breaking reality out there in the cosmos is where the true mystery tightens into a hard, scientific knot. The simulations are telling us, with increasing clarity, that our standard model of galaxy cluster evolution is incomplete. Some vital ingredient is missing from the recipe, a physical process we have not yet accounted for, or a wild initial condition our models do not allow. Every time the simulation fails to recreate this knot, it is not a failure of the computer, it is a clue. The universe is showing us a phenomenon that pushes computational astrophysics to its absolute limits, revealing that the most fascinating stories are written in the discrepancies, in the places where our best virtual universes simply cannot keep up with reality's boundless imagination. The knot's defiance of our best simulations inevitably leads to a more radical line of thought. Could its impossible properties be a sign that our fundamental physics is wrong? This is not a question scientists ask lightly, but when an object stands so far outside every prediction, it becomes a legitimate testing ground for exotic ideas. The first and most profound puzzle is dark matter itself. Our entire model of cosmic structure rests on the assumption that dark matter is cold and collisionless, meaning its particles interact only through gravity, passing through each other like ghosts. This is the bedrock of lambda CDM cosmology. But what if dark matter is not so simple? Some theorists propose a model called self-interacting dark matter. In this scenario, dark matter particles could occasionally bump into one another, creating a kind of friction within a dense knot like this. Such interactions could dramatically alter the cluster's core. Self-interacting dark matter would smooth out the central density peak, potentially changing how gas cools and flows inward. It could even transfer energy, subtly heating the core in a way that standard cold dark matter cannot. The knot's bizarre cooling flow and star formation might be the first visible signature of dark matter's hidden social life. Another radical departure targets gravity itself. For decades, a minority of physicists have championed theories of modified gravity, most notably MOND, or modified Newtonian dynamics. This framework suggests that on the vast scales of galaxies and clusters, gravity behaves differently than Einstein's equations predict, eliminating the need for dark matter entirely. Proponents might argue that the extreme gravitational field of this knot is precisely where MOND's effects would be most pronounced, potentially explaining its anomalous mass, distribution, and the dynamics of its galaxies without invoking an invisible substance. While most astronomers find the evidence for dark matter overwhelming, the sheer extremity of this object forces a re-examination of even our most cherished assumptions. Could it be a laboratory where gravity's rules are subtly rewritten? A third speculative idea reaches back to the universe's first second. What if the seed for this monstrous knot was not a quantum ripple, but a primordial black hole? These are hypothetical black holes not formed from dying stars, but forged in the intense pressures of the Big Bang itself. A single, stupendously massive primordial black hole, perhaps millions of times the Sun's mass, could have anchored this region of space from the very beginning. Acting as a pre-made gravitational nucleus, it would have drawn in matter at an accelerated rate, creating an overdensity that grew faster and became more extreme than anything seeded by dark matter alone. Its presence could also stir and heat the central gas in unique ways, disrupting the standard feedback loop. Each of these ideas, self-interacting dark matter, modified gravity, primordial black holes, exists on the fringe of mainstream astrophysics. The vast majority of researchers are deeply committed to finding an explanation within the established laws of physics, often through more complex but conventional mechanisms like chaotic mergers or magnetic insulation. Yet the persistent, glaring contradiction of this cosmic knot serves a vital purpose. It is a stress test for our entire understanding of the cosmos. When our simulations fail so spectacularly to replicate reality, it is not a cause for despair, but a beacon. It illuminates the boundaries of our knowledge and compels us to ask the hardest questions. Whether the final answer lies in a subtle detail we have overlooked or a revolution in physics we have not yet conceived, this mysterious knot is tightening the noose around our complacency, proving that the universe still holds profound secrets in its darkest tangles. Determining the age of this cosmic knot is like trying to read a clock that has been shattered and glued back together. We must piece together its timeline from 3 distinct forms of evidence, each a different type of cosmic clock. The first clue comes from the stars themselves. By analyzing the light from the galaxies within the knot, particularly the massive central galaxy, astronomers can perform a kind of stellar archaeology. The color and spectrum of that light reveal the mix of star ages. A population dominated by old, red giant stars suggests a system that formed its stars long ago and has been quiet since. A blaze of blue light from hot, massive stars screams of recent, violent birth. The Phoenix knot's core shows both in a baffling combination. It has the underlying red glow of an ancient stellar foundation, billions of years old, but superimposed on that is the brilliant blue, signature of a stellar baby boom happening right now. This tells us the knot itself is an old structure, but it is currently experiencing a dramatic rebirth. A second act of star formation so intense it outshines its own ancient history. The second clock is written in the chemistry of the hot gas. As stars live and die, they forge heavy elements like iron, silicon, and oxygen in their cores, and then expel them into space through stellar winds and supernova explosions. Over cosmic time, the gas in a cluster becomes enriched with these metals. Measuring the metallicity, the abundance of these heavy elements in the intracluster medium gives us a record of how many generations of stars have lived and died in that neighborhood. A very high metallicity suggests a long, prolific history of star formation. The gas in this knot shows significant enrichment, confirming that this is not a pristine, newborn structure. It has been hosting star-forming galaxies for a very long time. Yet the sheer amount of cool, metal-rich gas now raining into the center also indicates that this chemical recycling is happening at a ferocious, accelerated pace. The metals produced in one stellar generation are being quickly incorporated into the next, a cycle spinning wildly out of control. The third clock is dynamical, read from the motions of the knot's thousands of member galaxies. Are they moving on calm, settled orbits, or are their paths chaotic and unsettled? A mature, relaxed cluster has galaxies orbiting in a state of virial equilibrium, a balanced gravitational dance that takes billions of years to establish. Observations of galaxy velocities within this knot, however, show signs of significant substructure and unsettled motion. This hints that it may still be digesting a recent major merger, or that fresh galaxies are continuously streaming in along cosmic web filaments, constantly stirring the pot. This dynamical youth contradicts the ancient stellar populations revealed by the first clock, creating a chronological puzzle. So, which timeline is correct? The evidence paints a portrait of a cosmic entity with a deeply layered history. It likely began forming very early in the universe, gathering its first galaxies over 10 billion years ago, which explains its foundational mass and the old stars in its core. But then, relatively recently in cosmic terms, something dramatic happened. It either experienced a colossal merger or began siphoning matter from the cosmic web at an unprecedented rate. This event injected a vast new supply of cool gas into its core, reigniting star formation on a scale not seen since the universe's infancy. What we are witnessing, then, is not a stable configuration. It is almost certainly a temporary, violent phase, a spectacular but short-lived outburst in the multi-billion-year life of a cluster. This realization is crucial. If this extreme state is just a fleeting cosmic tantrum, a rare snapshot of a cluster hitting a turbulent peak, then it might simply be a fascinating oddity. But if our models predict such phases should be even rarer than what we observe, or should not be this extreme at all, then this knot becomes a signpost. It points to a flaw in our understanding of how often and how violently the universe's largest structures can reignite, challenging the very timeline of cosmic evolution we have so carefully constructed. A complete picture of this anomaly requires seeing it through every eye we possess. Each wavelength of light acts as a different filter, revealing a separate layer of its impossible reality. In the crisp optical view of the Hubble Space Telescope, we see the knot's cities of light. Thousands of galaxies swarm like golden bees, their spiral arms and elliptical halos painted in stunning detail. The central galaxy blazes with a brilliant blue core, a visual confirmation of the stellar frenzy within, surrounded by the faint, distorted arcs of gravitationally lensed galaxies from the far distant past. This is the portrait of structure, of the assembled matter. Switch to the piercing gaze of the Chandra X-ray Observatory, and the serene starscape transforms into a scene of violent energy. The space between those galaxies is not dark, but filled with a seething, luminous fog of 50 million degree gas. The image shows a blazing central core, intricate cavities carved by the black hole's jets, and vast, smooth halos of plasma that trace the immense gravitational well. This is the portrait of heat, of the energy that should be stabilizing the entire system. Then tune into the radio spectrum with instruments like the Very Large Array, or ALMA. Here, the knot whispers in a different language. We detect the faint synchrotron glow from relativistic electrons spiraling along immense magnetic field lines, tracing a vast, invisible web that permeates the hot gas. We see the focused beams of radio emissions spewing from the central black hole, jets that stretch far beyond the cluster's core, proving the AGN is active, but perhaps firing into empty space. This is the portrait of force, of the magnetic and particle dynamics orchestrating the chaos from behind the curtain. Finally, look at the microwave sky through the lenses of the Planck satellite or the Atacama Cosmology Telescope. Here, you see the shadow. The knot appears as a cold patch against the uniform glow of the cosmic microwave background, a Sunyaev-Zeldovich imprint caused by the hot cluster gas scattering the ancient photons. This is the portrait of mass, a direct measure of the knot's gravitational footprint on the very fabric of the universe. Alone, each of these portraits tells a compelling but incomplete story. Hubble shows a star-forming marvel. Chandra shows a cooling catastrophe. Radio telescopes show a powerful but misaligned engine. Microwave surveys confirm a gravitational titan. It is only when we layer these images together, creating a full multi-wavelength portrait, that the true, confounding nature of the knot snaps into focus. We see a system where extreme star formation coexists with scorching gas, where a roaring black hole cannot stop a cooling cascade, where immense mass hosts profound dynamical youth. The contradiction is not in one dataset. It is in the clash between all of them. The mystery does not simplify with more evidence. It deepens, tightening into a harder, more complex knot of physics that challenges us to find the single thread that can make this impossible portrait make sense. The knot's secrets will not remain hidden for long. A new generation of cosmic observatories is now turning its gaze towards this anomaly, armed with technologies that feel almost like science fiction. Leading the charge is the James Webb Space Telescope. With its colossal gold-coated mirror and infrared vision, Webb can peer through the obscuring dust and gas shrouding the knot's core. It will not just see the blue light of star formation, it will dissect it. By analyzing the infrared spectra of that light, Webb can measure the precise chemistry of the newborn stars, trace the motion of cold gas clouds as they spiral inward, and even detect the faint signatures of complex molecules, the building blocks of planets in that chaotic environment. It will tell us if this stellar frenzy is truly a new event or a sustained long-term condition, and whether the gas fueling it is pristine or recycled from previous generations of stars. This is a level of detail akin to moving from a blurry photograph of a raging forest fire to a thermal map showing every single burning ember and the exact path of the wind feeding the flames. While Webb studies the stellar output, another mission will diagnose the hot gas that is failing to stop it. The XRISM satellite, a joint Japanese and NASA mission, is an X-ray spectrometer of unprecedented precision. Imagine Chandra showed us the searing heat of the knot's plasma. XRISM will act as a cosmic blood test for that plasma. It can measure the velocity, density, temperature, and chemical composition of the hot gas with a fidelity never before possible. It will map the cooling filaments in exquisite detail, showing exactly where and how fast the million-degree gas is turning cold and falling inward. Most crucially, it might detect the subtle turbulence and energy injections from the black hole's jets, revealing why that heating is so ineffective. Is the energy being dissipated too quickly? Is it missing its target? XRISM's data will provide the hard numbers to finally model the broken feedback loop, transforming our qualitative confusion into a quantitative puzzle we can solve. On the ground, a different kind of hunter will soon begin its work. The Vera C. Rubin Observatory, with its gigantic 3.2 billion pixel camera, will not stare at one knot. It will scan the entire visible sky every few nights for a decade. Its primary mission is to create a dynamic, living map of the cosmos. In this vast cinematic survey, the Rubin Observatory will find more knots. It will identify hundreds, perhaps thousands, of massive galaxy clusters, and among them, it will flag the rare outliers, the ones with unusually bright cores or strange colors that mark them as potential phoenix-like anomalies. This statistical power is vital. Is our mysterious knot a true one in a trillion freak, or just the brightest example of a rare but important phase in cluster evolution? By finding a whole population of such objects, the Rubin Legacy Survey of Space and Time will tell us if we are studying a bizarre exception or a critical, misunderstood chapter in the universe's story. Looking further ahead, we may even learn to listen to the knot's creation. The Laser Interferometer, Space Antenna, or LISA, is a planned gravitational wave observatory that will float in space, forming a triangle with sides 2.5 million kilometers long. While current ground-based detectors like LIGO listen for the chirps of merging stellar black holes, LISA will tune into the lower frequency hum of the cosmos. It is designed to hear the mergers of supermassive black holes, events that would accompany the colossal cluster collisions that might have built our knot billions of years ago. Though the specific merger that formed this structure is long past, LISA will teach us the signature of such events. By hearing the gravitational wave soundtrack of other cosmic pile-ups, we can infer the violence and scale of the knot's own birth. It offers a chance to move from forensic reconstruction of a cold case to understanding the live dynamics of the crime itself. This one tangled knot has become a prime target for 21st century astronomy precisely because it embodies so many intersecting mysteries. It is a single object that demands the combined power of infrared, X-ray, optical, and gravitational wave astronomy to unravel. Each new instrument will not simply add more data, it will untwist a different strand of the problem. Webb will probe its stellar heart. XRISM will diagnose its feverish atmosphere. Rubin will find its family, and LISA may one day reveal its violent origin story. Together, they represent a convergence of technological might on a single, profound contradiction. The hunt is no longer about confirming the knot's strangeness, but about decoding its message, a message written in the broken rules of physics that might just redefine how we see the growth of everything in the cosmos. This single knot forces us to rewrite the biography of the universe's largest galaxies. The standard story for a brightest cluster galaxy, the titan at the heart of every massive knot, has been a simple tragedy of quenching. It forms stars in a glorious early burst. Then the supermassive black hole awakens, blasting out energy that heats the surrounding gas and shuts off the fuel supply forever. The galaxy enters a long, quiet retirement as a red and dead relic. It is a clean, linear narrative of birth, quenching, and death. But the Phoenix knot and its mysterious cousin are screaming that this biography is incomplete, perhaps even naive. They present a radical alternative, a story of resurrection. Here, a galaxy that should have been dead for billions of years has been violently reborn, its star-forming engines restarted at a ferocious pace. This means the life cycle of these cosmic giants is not a one-way street. Under the right, extreme conditions, the quenching process can fail, and the gas tap can be wrenched back open. The final state of a massive galaxy might not be a foregone conclusion dictated solely by its black hole, but the unpredictable outcome of a brutal, ongoing war between cooling and heating, where the tide of battle can, on rare occasions, completely reverse. If this extreme mode is a valid, if rare, chapter in a cluster's life, then our cosmic census must account for it. We have to ask a haunting question. How many of the massive, red and dead ellipticals we see in the nearby universe are actually sleeping giants with a hidden, violent past? How many went through a phoenix-like phase of catastrophic cooling and explosive rebirth billions of years ago before finally settling into their current quiet state? Their present serenity would be a mask, hiding a history of unimaginable stellar turmoil. This transforms our view of galaxy evolution from a steady progression to a saga punctuated by episodic, violent outbursts. The path to maturity for a giant galaxy may not be a gentle aging process, but a series of traumatic growth spurts and near-death experiences, driven by the chaotic inflow of matter along the cosmic web. The notch shows us that the universe's largest structures are not inert monuments, but dynamic, breathing entities capable of dramatic second acts. This directly challenges the core principle of self-regulation. For decades, the supermassive black hole has been seen as the ultimate governing mechanism, a thermostat that always kicks in to prevent a galaxy from over-consuming. The knot presents a scenario where that thermostat breaks, allowing the system to overheat in a very different way, with a frenzy of star formation instead of stifling heat. This implies there are limits to black hole feedback, thresholds of gas inflow that can overwhelm even this powerful regulatory engine. It suggests alternative pathways to a galaxy's final form. Perhaps some giants grow not through a steady accumulation of merged galaxies, but through brief, catastrophic feasts of cold gas, gorging themselves on stellar births before their black holes finally regain control. The existence of even one such object proves our models are missing a crucial variable, a recipe for chaos that can, under specific conditions, override the universe's standard rules of order. It forces astronomers to look at every quiet, red giant with a new suspicion, wondering what glorious and violent youth might be hidden beneath its calm, golden light. The ultimate significance of this knot depends entirely on its rarity. Is it a cosmic unicorn, a one-in-a-trillion statistical fluke that simply proves the rule? Or is it the first, brightest example of an entire hidden class of objects? The answer will either confine its mystery to a fascinating footnote or force a rewrite of our cosmic blueprints. To find out, astronomers are not looking deeper at this one object. They are stepping back to map the entire cosmic web with unprecedented scope and precision. Projects like the Dark Energy Spectroscopic Instrument, or DESI, are not taking pretty pictures. They are performing a galactic census on a staggering scale, capturing the spectra of tens of millions of galaxies and quasars. Each spectrum is a barcode, revealing not just what a galaxy is made of, but crucially, how fast it is moving away from us due to the universe's expansion. This creates a three-dimensional map of the cosmos, pinpointing the positions of galaxies across billions of light years. From this map, the underlying skeleton of dark matter, the true cosmic web, can be reconstructed. It is like using the glowing fireflies in a forest at night to deduce the shape of the invisible trees and branches between them. These vast surveys are the ultimate search engine for cosmic anomalies. By scanning such an enormous volume, they can finally answer the statistical question: how many knots of this extreme density and activity should exist, according to our standard model? And how many do we actually see? If the surveys find only one, our mysterious knot, then we can breathe a sigh of relieved confusion. It means our models of structure formation are mostly correct, but they must now account for the possibility of vanishingly rare, ultra-violent events. like a cosmic lottery with a single, universe-altering jackpot winner. But if the surveys begin to reveal a handful or even a dozen of similar hyperdense, hyperactive knots, the implications are revolutionary. It would mean our understanding of the web's statistical properties is fundamentally flawed. We have assumed the distribution of matter in the cosmos follows a predictable pattern, with most regions falling within a certain range of density and only the very tails of the probability curve producing true outliers. A population of hypernauts would mean those tails are far fatter and more populated than our theories allow. The cosmic web would not be a tapestry of gentle gradients, but a fabric woven with shockingly sharp peaks and profound troughs, a landscape of extremes. This would ripple through all of cosmology. The growth of these monstrous knots would have consumed matter from vaster regions of space than we thought possible, altering the timeline of structure formation in their vicinity. Their incredible gravity would act as more powerful lenses, bending our view of the distant universe in ways we haven't properly accounted for. Even our measurements of the universe's expansion and composition, which rely on assumptions about how matter is distributed on the largest scales, might need subtle but critical revisions. The hunt for other knots is not just about finding more curiosities. It is a direct test of whether our universe is as statistically tame as we believe, or if it harbors wild, unpredictable variations in its very architecture. The silence of the surveys so far is as telling as a discovery. If they find nothing else like it, the knot becomes a deeper, lonelier mystery. If they find a family, the mystery transforms into a new chapter of cosmology, one where the cosmic web is a far more dramatic and extreme place than we ever dared to imagine. This single cosmic knot is more than a mystery. It is a laboratory. Nature has constructed 5.7 billion light-years away, a testing ground for physics under conditions we could never hope to recreate on Earth. Within its confines, we find a staggering concentration of extreme phenomena all operating at once. Immense gravitational fields warp space-time itself. A turbulent, magnetized plasma seethes at 50 million degrees. Relativistic particles, accelerated to nearly the speed of light, scream along invisible magnetic highways, and at the core, a rampant firestorm of star formation defies every model of galactic aging. Each of these conditions represents a frontier of physics, and here they are, intertwined in a single, colossal experiment. On our planet, the most powerful particle colliders can only briefly mimic a fraction of this energy. Our most advanced plasma simulations are mere sketches compared to the chaotic reality of this million-light-year-wide cauldron. By observing this knot, astronomers are not just solving a puzzle, they are conducting observational experiments on a cosmic scale. They can stress-test our theories of magnetohydrodynamics, watching how magnetic fields channel and insulate unimaginably hot gas. They can study gas dynamics under the most violent gravitational tides, seeing how shock waves from mergers or black hole jets propagate through an ocean of plasma. They can witness black hole accretion and feedback in a regime of catastrophic failure, providing a brutal reality check for our computer models. Every flicker in its X-ray glow, every distortion in its lensed arcs, every twist in its radio jets is a data point in the universe's own advanced physics course. The insights gleaned here ripple outward, helping us understand other high-energy phenomena across the cosmos. The processes struggling for dominance in this knot, the chaotic cooling flows and the inefficient jet heating, are likely at play in the hearts of all massive galaxies, just in a more subdued form. By studying the system in its most extreme, unbalanced state, we gain a clearer picture of the fundamental forces that govern the life and death of galaxies everywhere. This knot, in its glorious contradiction, offers a masterclass in the physics of the impossible. Behind every dataset from this knot is a human story of obsession and frustration. The astronomer who first spotted its anomalous shadow in the Planck data likely spent weeks double-checking the calibration, convinced it was an error in the instrument, not a revolution in the sky. The team that directed Chandra toward those coordinates would have waited with bated breath for the data to stream back, only for their initial hypothesis to be shattered by the blaze of X-rays revealing a core in chaos. Picture a graduate student, bleary-eyed at 3 a.m. in a control room atop a mountain in Chile, meticulously adjusting the focus of a giant radio dish to capture the faint magnetic whisper from 5.7 billion light-years away. Each observation is a gamble, a request for precious telescope time that could yield nothing or could upend a career's worth of assumptions. The process is far from solitary. Unraveling this knot demands a global village of expertise. Observers from telescopes in Hawaii, Chile, and space send their raw data to theorists in Germany, Japan, and the United States. These theorists then craft new physical explanations, which they hand to computational astrophysicists running simulations on supercomputers in Switzerland and Texas. The cycle is constant, a feedback loop of prediction, observation, and confusion. Conference calls bridge a dozen time zones filled with the polite but firm clashes of competing interpretations. One scientist argues passionately that the magnetic data points to insulation as the key, while another counters that the velocity maps clearly show a recent, catastrophic merger. These debates are not academic theater. They are the sound of the scientific method grinding against a very hard problem. There is a particular, exhilarating brand of frustration unique to this work. A researcher might experience a genuine eureka moment, perhaps devising an elegant model where tangled magnetic fields perfectly explain the runaway cooling. They publish a paper, present it at a major conference to enthusiastic interest, and for a few months, it feels like the knot is finally yielding. Then, a new set of observations arrives from a freshly commissioned instrument. This new data reveals a detail the elegant model cannot explain, a subtle chemical signature or an unexpected temperature gradient. The elegant solution collapses, and the knot tightens once more, sending everyone back to their whiteboards. This cycle of hope and setback is not a sign of failure. It is the essential rhythm of cutting-edge discovery. It is a reminder that science does not march in a straight line toward truth, but stumbles toward it, corrected by the universe's own stubborn reality. What drives these teams through the long nights and the confounding results is a shared, profound curiosity. They are not just solving a technical puzzle. They are reading a chapter of the universe's autobiography that was thought to be lost. Every failed model teaches them what the universe is not. Every new observation narrows the possibilities of what it could be. The human story here is one of collective patience and stubborn wonder, a testament to our species' drive to look into the deepest dark and demand an explanation. The knot is not just an object in space, it is a mirror, reflecting our own relentless pursuit to understand our place in the cosmic web. And as the next generation of telescopes comes online, that human story is only just beginning its most exciting chapter. The knot's defiance leaves us not with answers, but with a cascade of deeper, more thrilling questions. Why is the cooling flow so catastrophically intense, creating a downpour of cold gas where our physics predicts only a gentle drizzle or none at all? What specific failure of cosmic engineering allows this cascade to overwhelm the system's natural defenses? We must confront the baffling inefficiency of the active galactic nucleus. Why are the jets from a billion solar mass black hole, engines of unimaginable power, so spectacularly ineffective at reheating the gas and shutting off the star formation? Is the black hole simply aimed wrong, its energy spewing uselessly into the void, or is the inflow of cold material simply too torrential for any feedback to stop? The knot's very existence poses a profound puzzle of origins. How did it assemble such staggering mass so quickly in the universe's history? Was it seeded by a primordial quantum anomaly, a 1 in a trillion density spike from the Big Bang itself, or forged in a cosmic pileup of multiple filaments colliding in a perfect storm of gravity? Each possibility challenges our standard timeline for how the cosmic web grows. Then there is the invisible architecture. Is dark matter, the hidden skeleton of the cosmos, behaving in an unexpected way here? Could self-interacting dark matter be smoothing the core or transferring heat, subtly altering the rules of the game in this dense environment? Or must we entertain an even more radical idea? Could there be an exotic, unknown source of energy or particle interaction at play within this tangled core? A physical process we have not yet dreamed of in our equations? These are not failures of science, but its brightest frontiers. Every unanswered question is a coordinate on a map of our own ignorance, a signpost pointing toward a richer, more complex universe than our textbooks describe. This knot, in all its impossible glory, is a masterclass in cosmic humility. It reminds us that the most profound discoveries often begin not with a solution, but with a better, more beautiful question. The mystery of this single tangled structure whispers that for all we have learned, the cosmos still holds depths of wonder we are only beginning to fathom. We have traveled from the grand architecture of the cosmic web down into the tangled heart of its most confounding knot. This journey reveals a universe far stranger and more dynamic than a simple map of stars. What began as a faint shadow on a microwave map unfolded into a cosmic titan that breaks not one rule, but several at once. Its staggering mass, its runaway cooling cascade, and its furious rebirth of stars collectively challenge the pillars of modern astrophysics, from our models of black hole feedback to our simulations of how the largest structures grow. This is not a minor puzzle. It is a system-wide contradiction written across 1,000,000 light years. Yet, this profound mystery is not a dead end. It is a beacon. Objects like this knot are the engines of scientific progress. They expose the edges of our understanding and compel us to build better tools, to conceive wilder ideas, and to look deeper into the dark. Every confounding data point is an invitation to learn something fundamentally new about the fabric of reality. The story of this knot is far from over. As the James Webb Space Telescope, XRISM, and the Vera C. Rubin Observatory turn their gaze toward this enigma and others like it, we stand on the brink of revelations that could reshape our cosmic biography. So keep looking up and stay curious. The universe is still writing its most thrilling chapters, not in textbooks, but in the tangled knots and brilliant filaments of the cosmic web. The greatest discoveries begin with a single, impossible detail. What will we find when we untangle the next one? Share your thoughts and questions below, and join us as we continue to explore space's deepest mysteries.